to Stream Boys. For right now, we're gonna watch Dr. Mike debate somebody about whatever. While I eat my food.
I remember taking a photo
There we go.
of one of the subjects. He came into the lab, showed his quads, and it was kind of wild visually how much larger the higher volume, lower intensity leg looked.
What a trip.
Yeah, and it's like, what was that? I think anyone that's spent more than a few years in the gym and had training partners and been part of like a gym community, people lifting, can acknowledge that not everyone's responding the same way.
Sure.
Over time.
Sure.
And I think part of that is how they train.
Cody Hahn, PhD. Welcome to the show.
Good to be here, man. Thank you for having me.
It's a huge honor. I knew you when you were an undergraduate at the same institution, ETSU, that I was a PhD student at. And I met you and we chatted a few times in the gym and things like that. And then later I was told you were in the master's program, and then later you went on to get a PhD and so on and so forth. And I followed your career, and just impressive is the only thing I have to say. The continuous amount of insight that you put out is like, I want to know what Cody has to say. And because of that, we got a dirigible, a blimp, a Zeppelin to pick you up. 2 weeks later, it dropped you off at our house. I hope the caviar was to your liking. Now it was good. It was fine. It was sufficient. Real quick, we already know you have a PhD in, what is exactly your PhD in?
Well, technically, the PhD is in kinesiology, but I concentrated in exercise physiology.
Exercise physiology.
And I worked in the molecular and applied science laboratory, managed and supervised and led by the one and only Dr. Michael Roberts.
Yes, of Auburn.
That's right, at Auburn University. Yeah.
Now, are you an Auburn football fan?
Sure. Yeah.
Ooh,
I mean,
careful, sure is not a sufficiently dedicated answer.
If you answered the question, someone's going to be upset, right?
That's true.
Yeah, I am. I'm originally from Tennessee, so go Vols, right?
Okay, good. Good street cred there.
Yeah, man.
You have lifted weights for a really long time. How long have you been lifting for?
Man, I started, I would say, resistance training.
Yes.
Under my father's tutelage with some ankle weights and calisthenics.
Cool.
Like he felt that was like the way to do things. And we did some bench pressing and curls when I was like 10.
Wow.
Yeah. But like really getting into it, like when I took my first scoop of creatine monohydrate.
Bye, natty stats.
Yep. That was at 14. So freshman in high school, that's when I really started getting into it.
That's when a lot of people start lifting.
Yeah.
Because you're like a kid before then.
And insecure.
Yeah. That part never left me.
Yeah.
Is there? Okay, excellent. We're on the same page.
Yeah.
All right. Science time?
Sure, man.
Science time. I have questions.
I'm excited.
Excellent. All right. So first question for you is sarcoplasmic hypertrophy. Sarcoplasmic hypertrophy sounds fancy and like a really cool science word.
Mm-hmm.
And if you're on a first date with some girl that went to NYU or something and she seems kind of like she thinks you're stupid, you can just say that. And she's like, oh my God, really? Like, tell me more.
Smart, yeah.
So smart. So there are, I think, two types of hypertrophy maybe, and one of them is sarcoplasmic. What is the sarcoplasm? What is sarcoplasmic hypertrophy, and what's the other kind, and why do we care?
Yeah, I've kind of been taking the title of the sarcoplasmic hypertrophy guy, which was not the intention of that research, was to answer a specific question.
Very long Instagram handle if you're going to put your hat on that.
Yeah, we can work on that. We can workshop it, Sarcoplasm Man or something, shorten it, Sarco Man, I don't know. But yeah, I think we should probably start with a lot of words are poorly defined, right? Sure. And I think hypertrophy in and of itself, or hypertrophy, as some people would say.
The hypertrophy.
Right.
Something you win for big muscles.
Right. I got really interested in that, like what is actually increasing in the muscle cell as it grows.
Yes.
And that was, so like the review article we published during my PhD at Auburn, it's in Frontiers in Physiology, really meant to help answer that question. It sounds silly. It sounds like, should we know what that is?
It's all just muscle, right?
Right. But it turns out, there wasn't a lot of good, I would say, intentional research on measuring more of the cellular morphology or the structures and proteins and organelles inside of the cell. There was a good amount of research, and we're talking about 5 years ago when we published that, and so I really wanted to survey the literature and see what do we know about what things change inside of the cells when they grow in response to resistance exercise. And the deeper that I got into the literature, there wasn't a lot of research on it.
A lot of speculation.
Yeah, a lot of speculation, and you would, see, increases in fiber cross-sectional area, right? Or increases in lean body mass from a DEXA scan.
Yeah, very big picture.
Yeah. Or do an ultrasound image, and if the thickness of the muscle increases, that's hypertrophy. And so what struck me from some of the training studies that we were doing at Auburn in the Massel, Brooks Mobley, he did a training study, and I was kind of like his right-hand man there. For that study, it was 2 semesters long, and we took muscle biopsies. There were almost 100 subjects in it.
Holy crap.
Yeah.
For folks tuning in, that's an unusual number of subjects for an exercise science study. Very high. You'd be lucky if you get 20.
Yeah, right. And, analyzing that data, I did a lot of the image analysis and the agreement between methods. So if you have a DEXA scan, lean body mass, or just appendicular lean mass, so just looking at the mass of the legs or the arms, and you see that increase, well, we would think that if you look at an ultrasound, that should increase alongside it, right? The thickness measurement. Or if we look at fiber cross-sectional area in the same muscle, well, that should increase alongside. They should all agree, and they didn't very well. And so that kind of sent me down this analysis of okay, well, why? But then moreover, what if we see a fiber? And when I say cross-sectional area, so let me back up a little bit. If we take a muscle biopsy,
which is ripping out a part of the muscle.
I brought a biopsy needle with me to do this on camera.
Scott, the video guy's ready.
Okay. All right, Scott. Come on out, man. No lidocaine. And so, we actually take muscle tissue out of the quadricep. And then for cross-sectional area, through a series of steps, we ultimately mount a very thin slice of muscle fibers onto a microscope slide, and we stain it, and we're able to visualize it using immunofluorescence microscopy. So you can see the membranes, you can see the myonuclei, you can see the muscle fibers in cross-section.
Right. Yeah. So it's a muscle cell, is this long thing, also called a muscle fiber. You cut it, and you look at it from the long way down, and then how big it is how much hypertrophy has maybe occurred. If it was smaller, then it was bigger. But then what about the contents? Do they all grow at the same rate, or did we just not know at that point?
You're on it. So it's okay, in cross-section, we see the cells get bigger. What went up?
Right. What are the options there? We have the myofibril itself, which is kind of like the actin myosin stuff that pulls. That's what does the work. But then we also have some mitochondria in there. If it's an endurance athlete's slower twitch muscle fiber cell, it's tons of mitochondria, not a lot of contractile apparatus. And then there's also the whole thing that all that sits in is called the sarcoplasm, like the soup of the cell. If anyone's ever seen an animal cell in cross section, you got like ribosomes in there, you got mitochondria in there, you got a nucleus somewhere. If it's a muscle cell, you have contractile material, but all that soup, that fluid, everything it's inside the cell, that's the sarcoplasm, correct? And so like if you grow a muscle cell, but
How we
the
doing, boys?
sarcoplasm increases, but you don't increase any of the contractile material, the actin myosin stuff, you're not going to get any stronger, probably, because there's no more ability to contract. But if you increase, maybe there's a way of training where if you increase the size of a cell a little bit, but way more contractile material and not a lot of the soupy stuff goes up, it'll look the same to someone else who's like, those two guys are equally as jacked. But if one guy has more myofibrillar hypertrophy versus sarcoplasmic hypertrophy, the sarcoplasmic hypertrophy is like what people used to say, and I am asking this question immediately after, is like back in the 80s, they surmised that bodybuilders who had big muscles, but weren't as strong as powerlifters for the muscle size they had, people would say, okay, the powerlifters have more myofibrils in the same size cell or even smaller, but the bodybuilders have maybe the same size myofibrils or a few less. They have tons of sarcoplasm. That soupy part is just pushing the cell out so big that they have these big, more or less useless muscles. Is that all bullshit, or is there some truth to that, or what the hell is really going on?
Cool.
Right. Well, I'm still trying to figure that out.
Okay. What do we know more?
Yeah, I think, and there's what we saw in our lab, and there's other researchers that are like interrogating these questions. So sarcoplasmic hypertrophy, just to like clearly define it, and you were, I think, largely
the
accurate
fifth grade
there.
version.
If we take that cross section, right, we have this fiber, which you said it was kind of like a cylindrical structure, which is what we used to think. And this is only in the last like 3 years that we've learned this. And Brian Glancy did some of this research using much more sophisticated microscopy work, showing it's more like a mesh. Myofibrils are more like a mesh, like a lattice network, instead of just like these cylindrical structures.
Okay.
That said, the myofibrillar sort of network, or cylinders, if you will, that run along the length of the fiber, there are the sarcomeres in there, the contractile proteins, that's where we're generating force. That probably occupies about 85% in general of that spatial environment.
Of the average muscle cell.
On
average skeletal muscle cell.
Yes, yes. All right. And so then the other 15%, what is that? And so probably about 10% of it is the sarcoplasm, which is this kind of fluid medium, this aqueous media that everything kind of moves through and is suspended in, right? And you've got enzymes and ribosomes and ions and all that stuff that's kind of floating around.
Soup-like.
Yeah, yeah. And so, and then, the sarcolemma, the actual membrane of the muscle fiber.
Yes,
right.
The outer covering of the muscle cell.
And then you've got your myonuclei. And one thing that makes muscle particularly interesting is that it's multinucleated. There are multiple nuclei that run along the length of the muscle fiber. And so sarcoplasmic hypertrophy, if that spatial environment and the structures within it are preserved in proportion as the cell grows, that would be conventional hypertrophy, right?
You get it all. More of everything.
Yeah.
That's how I order at the restaurant.
In proportion to how you started.
Yes.
So sarcoplasmic hypertrophy, therefore, would be a disproportionate increase in the sarcoplasm as the cell grows.
Yes.
Relative to its starting state, you see?
Yes. That's kind of like you have two different size options for soup at the restaurant, but they both have the same amount of meat. One just has more broth. And you're kind of like, are you guys ripping me off?
Your analogies are so great, man.
Right? Like, I miss maybe a little bit of that. But if by great you mean stupid and childish, I agree wholeheartedly.
Oh, that's a good analogy.
Right, but like, so you don't get any more of that meat. And I think that for bodybuilders, they don't really give a shit. Someone's like, that's all sarcoplasm. I'm like, oh yeah, watch this. Hey, whoa.
Right.
But with powerlifters...
If you've got some sarcoplasmic hypertrophy going on, I'd take some of that, buddy.
Exactly. It's just literally steroid oil. But anything practical for people to take away from the sarcoplasmic versus myofibrillar. Some people would say train for low reps, you get more myofibrillar stuff. You'll have a denser muscle, it'll be stronger for how big it is. Other people would say, look, all of these are probably transient changes, and that over the long term, whether you train for low reps or high reps, you're going to get the same degree of jackness and roughly the same degree of cellular contents anyway. What's your take on that?
Well, I think prematurely, and I'll mention Dr. Chris Phan again, because after the sarcoplasmic hypertrophy experiments and the reviews that I did at Auburn with Dr. Roberts, Chris went on to help address more of these questions, particularly loading, like heavier loads versus lighter loads,
Yes.
right? Kind of lower volume, higher intensity, higher volume, lower intensity within subject design. So one leg, which is really, it strengthens the study. And so it seemed, and again, using sophisticated methods, proteomics, it seemed that the higher intensity loading paradigm promoted more of an increase in myofibrillar protein abundance
Wow.
than the lighter loading paradigm. Now, it wasn't a night and day difference, but I remember taking a photo of one of the subjects that was like, came into the lab, like showed his quads, and it was kind of wild visually how much larger the higher volume, lower intensity leg looked. Yeah, and so, Dr. Roberts would call that like the eye test, and it's like, what was that, and so there's inter-individual differences, I think, that exist in how people will respond.
Sure.
And I think there's a lot of contention around how that's like statistically analyzed, and it's like fair enough. But I think anyone that's spent more than a few years in the gym and had training partners and been part of like a gym community, people lifting, can acknowledge that not everyone's responding the same way
Sure.
over time.
Sure.
And I think part of that is how they train.
Yeah.
Right? What are they doing? Now, practical application. I think that it's fair to hypothesize that if you lift with heavier loads relative to your capacity,
That's a 5 to 10 versus like 20 to 30 or something.
Yeah, that's probably we'll say, less ambiguous signal to your cell of what you want it to do. Make more of the mechanotransduction machinery, the contractile machinery.
Yes.
Right, because that's really what we're doing when we're training. We're telling our nuclei to transcribe genes.
Yes.
Which genes are we telling them to transcribe?
Right.
What are the signals, right?
Right.
And I think those signals are specific. And I think that if you're loading heavier, a lot more tension experienced in compressive forces in the fibers, that it would make sense that the contractile apparatus, the proteins that make up the, thick and thin filaments and that connect that myofibrillar sort of mesh to the membrane, because that's interesting, right? There's proteins that actually connect it, right? It would make sense you would make more of those, but then if you train more, again, in that more glycolytic system, so
15,
we're talking
20, 25 reps.
yeah, somewhere in there. Probably see more of the response that I saw like in my dissertation work, right? More glycolytic enzymes, more of those sarcoplasmic reticulum proteins.
And more of all proteins, of course. You still get growth in the contractile proteins, but fractionally less than you would expect if you did lots of sets of 5 to 10, for example.
Yeah.
Does this, in your mind, give you some insight into very hypothetical periodization model where you train for high volumes with higher reps for a while, and then you have a lot of architecture built and the cell has expanded, and then maybe if you train that same muscle with heavier loads, that's a 5 to 10, you kind of fill in the contractile machinery, backfilling? Is that...
And this is where, like, if depending on the strength of my answer and how confident I am in it, like especially in the scientific community, like a lot of the people who are researching this would get really worked up because it's like an extrapolation of like limited evidence to the and so like carefully, I would say with much more work to do, and a lot of respect to other labs who found different things than us.
Sure.
we could be wrong.
Sure, of course.
Maybe we did something wrong. I don't think so. I think that we were very careful.
Yeah.
And I've seek the truth the whole time.
Sure,
like, I
of
don't
course.
have a dog in the race other than like I want to know the truth.
Other than that 1897 dog.
Other than that one, and RIP, thank you for donating tissue to science.
Yes.
But I think, man, I mean, and what I actually tend to do with people that I work with on their programming that are trying to maximize muscle growth, I feel comfortable organizing training into periods of higher volume or sprinkling it in a phase, or emphasizing it rather during a certain phase primarily, and then shifting into more of a heavier load for a similar amount of time, or at least maybe like half of the time that so if you did 3 months of like sets of, we'll say 6 to 12 reps, and then you had, I really like the I don't know how far we want to get into like programming, but sort of like I think Brett Contreras has called this sort of idea the rule of thirds, where it's just like it is, you train within a lower rep scheme for some of your work, and then an intermediate rep scheme, and then kind of that higher rep work, right? You're kind of checking all those boxes within a session chronically. So within the session, it might look something like that, right? Where you do, for a squat, for example, let's do a set of 3 to 5. And then for, perhaps if we're talking about the quads, a rear foot elevated squat or a leg extension even, in that intermediate rep range. And then perhaps you finish with like some light lunges where you just do like 30. So we're kind of surfing the curve there, right? Of like that repetition continuum, and using different loads within those different rep ranges
to check all the boxes of the different ways in which muscle grows.
And that's like what it could look like within a session, but how you might periodize it is something like that, right? Where it's just like maybe 1 month or 4 to 6 weeks, we really lean into that 3 to 8. I really don't like putting like a fixed number on this stuff.
Heavier.
Yeah, heavier. And then perhaps the next month we go more 8 to 12, and then, you see what I'm saying?
Sure.
And then we do more. It's not like we never do these other things like vertical and horizontal integration, some people would call this, across the annual plan. But you see what I mean? You might do it that way.
Sure.
And I think the variation is also something that's useful for people to keep people engaged.
Of course.
Yeah.
You never just, it's unlikely you're ever going to train only for low reps or only for high reps if you want your best gains. Because just for psychological variation, it gets boring to do the same thing over time.
Right.
Yeah. All right. Next topic. We could talk about that for like the next several years.
Yeah.
Muscle fiber type transitions with exercise training.
Okay.
So we have, I am not a big fan of 2A, 2X, 1, whatever the fuck. I consider that nomenclature wildly outdated and on principle excessively simplistic. I like to, and there's lots of evidence confirming this, see fiber type as largely spectral in nature. There's a spectrum of faster twitch fibers all the way to slower twitch fibers and everything in between. Can you tell us the story about how when someone just starts training, what happens to their fiber types? And also, are there any things or ways of training that we can employ that will change our fiber type at least a little bit into the direction of the kind that grow bigger? Because from what I understand, when you first start training, because your muscles are very untrained, hilariously, they're more faster twitch than slower twitch, just chilling. And so as you train for muscle growth, your muscles get bigger, but it seems that they behave more and more like slower twitch muscle fibers. And the slower twitch fibers also don't grow as much, though they do grow, as the faster twitch fibers. So we have a bit of a conundrum, where as we train for weeks and weeks and months, we're getting bigger, but our proneness to getting even bigger starts to decline a little bit because our fiber types are shifting over to be slower twitch, and those aren't the kind that grow the most. The faster twitch ones do. That does explain, at least in part, the phenomenon of newbie gains pretty well, because like if you're all damn near pure fast twitch, you're going to grow a fuckload. But as you get more and more slower twitch, you're like an endurance runner kind of, and they don't hardly grow from shit. They just kind of like do work, and I don't know where that all goes. But then people have the question of, okay, now that I've been training for months or years, is there any way for me to get the fibers to shift back to faster twitch without losing a ton of them, so that I can get another bump of growth? That's the conventional question and story I'm familiar with. What do you have to say about the matter? Does any of that make sense to you? Or is it all like, nah, that all just ends up in the wash?
Well, and you just had Daniel Plotkin here, who's the first author on the muscle fiber type, shifting perspectives paper, and I think that was a really good piece of work there. I mean, and he really summarized the literature well.
We didn't talk at all about that, by the way.
Okay.
Yep. So you're going to have to talk.
Well,
instead.
I want to definitely give credit where it's due.
Sure,
right?
sure.
Like he could probably explain this much better. But
Okay.
I mean, what you said, man, is some themes, right? It's like, okay, someone's untrained and they have relatively small muscle fibers. Those muscle fibers, let's start with this, right? So for a number of years, I mean, really, Dr. Andy Galpin, I think, helped to really clarify some of this using single fiber isolation techniques and looking within individual muscle fibers.
Which is important to get really deeply at the heart of the matter.
Yeah, yeah. And so there's just been different methods used to classify. We like to dichotomize things, right? We like to make things like it's black or it's white, or it's
Fast
right
or
or it's
slow,
wrong, or it's yes or it's no. And a lot, like most things are kind of on a continuum, right? Like a grayscale. And so like fiber types for a long time where it was like type 2, type 1, maybe there's subtypes like type 2A, type 2X. But the methods used, I think, had some serious limitations.
Yeah.
Right? And it's just like, okay, we're taking a tiny chunk of muscle out of this. By the way, that is a notable limitation in the exercise science literature. Like I did a lot of biopsies, really cool technique. We can learn a lot. It's been solid in a lot of ways. However, dude, most of that literature is from this muscle right here. Like 150 milligrams of samples.
That small part of that muscle right there.
It's just like, and we have some other biopsy data, but like most of it's right here. It's just like, well, is this
representative of the whole human body?
Right.
Maybe not.
Right. And so, okay. But if we just look at a lot of the research on that guy, we used to use that sort of classification system. And I think just to kind of boil this down to sort of maybe